Okay, so I wanted to do a few examples of a very similar, related, almost identical concept, but for cases where we see numbers in the denominator. So the first few examples we did, notice that the numbers, there were no fractions. They were all integer bases. But now we're looking at some examples that have these fractional bases. So this one, for example, says 1 over 1024, and this one says 1 over 256. So here's the thing. We want to solve this, so it's going to be pretty much the exact same start. So this would be 1 over 1024 to the x plus 9 is equal to 1 over 256 to the negative 5x plus 5. So again, if we want to solve an equation like this, we're going to look for common bases. So our table is going to be really helpful here. So I'm going to try to find a column where I see the numbers 1024 and 256. So I'm going through, and obviously that one's all 1. To be honest, you will never use that row. Actually, yeah, hardly. You'll probably never use that row. I don't see, so I do see, actually I see both numbers right here, 1024 and 256. So I can go back into my equation now, and I can rewrite it as 1 over, what's 1024? 2 to the 10th power? 2 to the 10th power to the x plus 9 equals, and 256 is 2 to the 8th, 1 over 2 to the 8th to the negative 5x plus 5. Okay, so when we were going over the exponent rules, there was one very important rule that had to do with negative exponents. So if you remember, there was a rule that said x to the negative a power is equal to, it just becomes a fraction and it goes to the denominator. So notice that we started with a negative power, negative a, and in order to get rid of that negative, we threw it in the denominator. So now it's down here, and notice that the a is now positive, not negative. So it also works the other way as well. Let's say you had a fraction like we do here, where you have the negative power in the bottom. The way you can get rid of that is throw it back up top. So that's the trick we're going to need in this scenario. So if I look here, I see 1 over 2 to the 10th power. Notice that 2 to the 10th power is in the denominator. So I can fix that. I can bring it up by just changing the sign of that power. So I'm going to put negative, and I'm going to do it in a different color to be intentional. So 2 to the negative 10th power to the x plus 9 is equal to, let me get rid of this stuff over here. Yeah. Okay, that's that side. And then this one, again, notice that it's 2 to the 8th on the bottom. So if I want to bring that up, I can put 2 to the negative 8th power to the negative 5x plus 5. Okay, so again, I want you to realize that process-wise, table-wise, everything-wise, exact same process as what we did over here. Find the right place in the table, rewrite with a common base. The only thing that we're adding for these ones is the numbers sometimes appear in the denominator. So when you bring them up, you have to make sure to express them as negative numbers. So here's a negative and a negative. Now, everything else after this is pretty much the same. Remember how once we got the common base, now we have 2 as the base. we really don't care about that part anymore because that part is already equal. Now we're trying to make the rest equal. So once we do that, we're trying to see where does this exponent equal this exponent. Actually, before I do that, it's probably a good idea to do this, to apply the power rule. So remember if we have, x to the a and we tag on another power, we would multiply those two powers together. So same thing here. If I want to write this in a slightly simpler way, I could do this. Negative 10 times x plus 9 is equal to 2 times negative 8 to the negative 5x plus 5. And with that, you will see that we can get rid of the common base. So the 2 is not really needed anymore. So if I wanted to solve this equation, I would just pretty much throw I would just pretty much throw an equal sign in between. So I'm trying to solve this. Negative 10 times x plus 9 is equal to negative 8 times negative 5x plus 5. If I distribute, I'll get negative 10x minus 90 is equal to 40x minus 40. And then same process as before. I see these are like terms right here. So I'm going to add 10x. That will go away. So I get negative 90 is equal to 50x minus 40. Let me move these real quick so I have more space. Move. I rearrange them right now. And then I see that these are like terms, the negative 90 and the negative 40. So I'm going to add 40 to this side. And then I get negative 50 is equal to 50x. If I divide by 50, I'll get x equals negative 1. Okay, so again, very, 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 very similar process. Just throwing in that when we have denominators involved, we're going to express it as negative powers. So I'll go ahead and do one more. Let me just clean this up really quick. So here, let's say I was going to do this problem. And I'll go ahead and save that one. Yeah, let me throw this one down here. Let's see. Okay, so let's say we were working on this problem now. So notice this one has a combo. So I see one that has a denominator. I see one that looks just like the example types that we did before this one. So I can still go into my table and I can still find both these numbers expressed. So I can still look for 64 and I can still look for 16. So I'm going to go to my table. Let me blow it up real quick. So let's see. I'm looking for 64 and 16. So we already know this one, not so much. This one, 16, 64. So that looks like a winner. So let me go ahead and rewrite this fraction. So I can rewrite it as 1 over, according to this, 64 is 2 to the 6th power. So 2 to the 6th power to the negative 4x minus 13 is equal to 16. According to this is 2 to the 4th to the 2x plus 5. Okay. So in the first example, both of these were fractions. So because they were both fractions, I needed 2 negative exponents. But in this case, I only see one that has the denominator. So I only need to write one of these as a negative exponent. So I'm going to write this as 2. Again, I'm purposely changing the color so you can see I'm making the exponent negative to show that it came from the denominator. Equals, and then this one's already good to go. Okay, and then again, I can apply power rule. So what does the power rule say? If I have some exponent to another exponent, I'm just going to multiply those together. So that would mean these get multiplied and those get multiplied. So let me show you how that works in the next step. So the base, obviously I did all that work to get the base the same. So I'm going to leave it as 2, but when I write the power, it's going to all come together. So that's 1 power is equal to 2. And there's the other power. So you know that you can ignore the base once it's common. So I'm no longer doing work to try to get those to be the same. Now I need to work on the powers being the same. So I'm going to go ahead and ignore. Oops. I'm going to ignore. And then I'm going to focus just on setting those equal to each other. So this will be -6 times -4x minus 13 is equal to 4 times 2x plus 5. Again, if I distribute, that'll be 24x. That'll be 78. It's equal to, distribute on this side, 8x plus 20. Looking for families, so 24x and 8x. I tend to move the smaller one, but it's really up to you which one you want to move. Okay, I still have space. That becomes 0. So I get 16x plus 78 equals 20. Now I see these are like terms, the 78 and the 20. I already have the x alone on one side, so I'm going to bring this over here. And sorry, let me erase this so you don't think it's division. That will go away. So I get 16x is equal to -58. Hold on, I'm just checking. So -58 divided by 16 divided by 16. That will just become 1. And so I get x is equal to -58 over 16. Which seems ugly, but I don't think I made a mistake. Let me check real quick. -6, 24x plus 78, 8x plus 20, 16x minus 58. Nope, looks right. So just keep in mind this can be reduced by definitely 2. So -29 over 8. I think that's as far as we can go. So that would be my answer, -29 over 8. Yep. All right, that should do it.